In this mini lecture, I'm going to talk about rationalizing the denominator of a radical expression. And what happens is there are many times in mathematics where we need to rewrite an expression so that it does not have a radical in the denominator of the fraction. And so this process, how we do that sort of depends how many terms are in the denominator. So this only applies if there's a radical in the denominator. And what we look at then, if there's just one term in the denominator, that's not too bad. And this example here sort of shows how that works. If I have 7 over the square root of 2, the problem again is I've got this radical square root in the denominator. But that's pretty easily accomplished here, getting rid of it, if I just multiply the bottom by the square root of 2, because the square root of 2 times the square root of 2 is just 2. But whatever I do to the bottom, I have to do to the top. And in particular, what's happening here then, when I have square root of 2 over square root of 2, of course, that's just equal to 1. So when I multiply by that, it doesn't change the value of the fraction. The value of the fraction stays the same. What I end up with then, though, is 7 times the square root of 2 in the numerator and just 2 in the denominator. Another way of thinking of that, too, square root of 2 times square root of 2 would be square root of 4. But then the square root of 4 is just 2. And so what happened is I shifted the radical in the denominator to be a radical in the numerator. Also, some other stuff changed, but that's that idea. Now, what we call this at the beginning, this square root of 2 in the denominator, square root of 2 is an irrational number. It can't be written as an exact fraction with just integers, like 3 over 4 or 7 over 2 or anything like that. Square root of 2 is an irrational number. If I wrote it as a decimal, if I did it on a calculator, the decimal would go on forever without falling into any sort of repeating pattern. At the end of the problem, I still have an irrational number, but now that's in the numerator, and my denominator now is just 2, which is a rational number, 2 over 1. And so what we say is we've rationalized the denominator. We changed the denominator from an irrational number to a rational number. And there's times where that ends up being important in other math classes. Way back when, this was important before calculators, because since the square root of 2 is an infinite decimal, dividing 7 by the square root of 2, you would have had to write 7 divided by this square root of 2, which is approximately 1.414, but it goes on forever. And this division problem is hard to do by hand, right? Where you have all these decimals, and we don't know how many decimals we have to try to write here to get a certain level of accuracy in my answer. However, with this case now, I've got my long decimal on the inside, and I just have 2 on the outside, right? I've got this 7 times the square root of 2 is some big long decimal, and the 2 that I'm dividing by is just outside, and this is relatively easy to do. So historically, that's one reason we used to rationalize the denominator. There are other kinds of things we sometimes need to accomplish, though, where this process is still required. So let's look at a couple examples here. Rationalize the denominator and simplify. Assume that all variables represent positive real numbers. That just means I don't have to worry about absolute value bars or anything like that. So what I look at here, 12 over the square root of 3, what can I multiply square root of 3 by to get a perfect square? Well, square root of 3 times square root of 3 would be pretty nice. That would just be the square root of 9, which would be 3. So I'm going to multiply the bottom by the square root of 3, but whatever I do to the bottom, I have to do to the top. So in the top, I get 12 times the square root of 3. The bottom, square root of 3 times square root of 3 is just 3. And now I look to see, can I simplify it all? Well, 3 goes into itself once. 3 goes into 12 4 times. So I'm left with 4 square root of 3 over 1. But normally I don't write over 1, so the answer would just be 4 times the square root of 3. In this next example, something just as simple can happen here. How could I get rid of this square root of 6? Now, there's a square root of 7 in the numerator as well. That's also irrational, but I don't really care about that. I care about the square root of 6. So when I look at this, then I'm going to multiply the bottom by the square root of 6, but then I've got to do the top by the square root of 6. Now here, when I'm multiplying these square roots together, their insides have to get multiplied. So I'm going to get 7 times 6 is 42. And then square root of 6 times square root of 6 is just 6. I certainly can simplify here. 2 goes into itself once. 2 goes into 6 3 times. So I would just get the square root, of 42 divided by 3. Now, I can divide 42 by 3. 3 goes into 42 14 times. But this 42 is inside of the square root. I can't cancel something inside a square root with something outside a square root. So I can't do any canceling like that. There is a chance that I could still simplify this problem a little more. You would ask, is there a perfect square that divides into 42? I want to at least think about that. What are some perfect squares here? Well, 2 squared is 4. 4 doesn't go into 42. 3 squared is 9. 9 doesn't go into 42. 4 squared is 16. 16 doesn't go into 42. 5 squared is 25. 25 doesn't go into 42. That's already more than half of 42, so I don't have to check anything else. So in this case, no. There is no perfect square that goes into 42, so there's no more simplifying that can happen, and I would be done. Let's do a few more examples here. So, square root of 49 over 2x. One thing here, when I've got a square root with a fraction bar inside, I can split that into 2 separate square roots, just like with multiplying. So I can make that the square root of 49 over the square root of 2x. And of course, the square root of 49 is just 7. Now I still have the square root of 2x in the bottom. I would like to get rid of that square root. To get rid of the square root, I'd like to turn it into a perfect square. And so what I'm going to do is I'm going to multiply by that same square root. And so in the top, I get 7 times the square root of 2x. In the bottom, if I take a square root times itself, that always cancels out, right? So I'm just going to be left with the inside 2x. The other way you could think about it, 2 times 2 is 4. X times x is x squared, so that would be the square root of 4x squared, which is again 2x. We could do it either way. I can't cancel anything inside a root with anything outside a root, so I'm done here. If the 2 went into the 7, I could cancel the 7 and the 2, but that doesn't happen. Okay, a couple more sort of special cases. In this next example, part D, square root of 24y. I could multiply just top and bottom by the square root of 24y, but I'm using a bigger number than I really need to. Part of the thing here is that the square root of 24 can be simplified. There's a perfect square that goes into 24, right? 2 squared is 4, and 4 divides into 24 6 times. And what's usually best is to go ahead and simplify any radicals that you can simplify first. So I'm going to rewrite the 24 as 4 times 6. And so I know I can take the square root of 4 and get just 2. And now I can cancel 2 goes into itself once, 2 goes into 6 3 times. Remember, I can't cancel anything inside a root with anything outside a root. So I couldn't cancel these 6's. That wouldn't be allowed. But I can cancel the outside 2 with the outside 6. And now what I can do is I'll just clean this up. Now I can multiply bottom and top by the square root of 6y. And so I get 3 times the square root of 6y over 6y. And again, I can't cancel the 6's, but I can cancel the 3 with this 6. So 3 goes into itself once, 3 goes into 6 twice. So I just get the square root of 6y all over 2y. There is another way this problem could be approached. I don't think it's worth thinking about here. This is the easiest way of doing it. All right, and this last one, this is a little different because it's a cube root here, right? It's the cube root of 5. So if I just multiply the cube by the cube root of 5 again, in the top and bottom, this would be 20 times the cube root of 5 over the cube root. 5 times 5 is 25. And the problem is, I don't know what the cube root of 25 is. If this were a square root, this would work fine like it did in all these other examples. But since this is a cube root, that's not going to work. So I'm going to get rid of this stuff here. That's wrong. What I'm going to have to do to get rid of a cube root, I need a perfect cube. So I'm going to multiply the bottom by the cube root of 5, but that's just, it's sort of messy there. And then whatever I do to the bottom, I have to do to the top. But I'm actually going to have to multiply by the cube root of 5 again. I need 3 things that are the same to get rid of a perfect cube. One way I could write this then, I'd have 20 in the top, 5 times 5 is 25 in the bottom, and in the top in the radical, and in the bottom here I get 5 times 5 times 5, which is 5 to the 3rd power. And as long as these exponents correspond, they cancel each other out. So I'd get 20 times the cube root of 25 all over 5. Another way you could look at that, if you did this here, 5 times 5 times 5 is 125, and the cube root of 125 is 5. That's another way you could think about that calculation going. What I do then, remember I can't cancel inside with outside, but I can cancel 2 things that are outside with each other. So I can say 5 goes into itself once, 5 goes into 24 times, and so my answer would be 4 times the cube root of 25 all over 1, or just 4 times the cube root of 25. All right, so that pretty much takes care of the case where I just have one term in the denominator. If I have 2 terms in the denominator, it becomes a little more involved. Now, as long as I only have square roots in the denominator, like I do here, I just have the square root of 6, that's not too bad to deal with. If there are cube roots or other roots, it gets much more complicated, and we're not going to deal with that case in this class. So what we end up doing in this case, when we have 2 terms in the denominator and at least one of them has a square root, we multiply top and bottom by what's called the conjugate of the denominator, and we'll talk more about that later. So here I've got 4 plus the square root of 6. That's what I started with. And what I multiply then is 4 minus the square root of 6 in the top and the bottom. And so in the top, I've just got 30 times 4 minus the square root of 6. Now, I could distribute here, but I would suggest waiting. When you just have a single term in the numerator, it's usually best not distributing too quickly. In the bottom, I am going to do FOIL. So first, 4 times 4 is the 16. Outer, I get the first 4 and the last square root of 6, but that's a negative. So it's minus 4 square root of 6. And then inner, That's positive square root of 6 times 4, so that's plus 4 times the square root of 6. And then last, positive times negative is negative. Square root of 6 times square root of 6 is 6. Right? That always works that way. You could also say 6 times 6 is 36. The square root of 36 is 6. But that's sort of extra steps. What happens then in here, these middle terms cancel out. Right? One's negative and one's positive. So I just get 16 minus 6 is 10 in the bottom. Now what happens here, I can cancel 10 goes into itself once, 10 goes into 33 times. So I end up just getting 3 times 4 minus the square root of 6. And now I distribute and get 12 minus 3 times the square root of 6. So I had a radical in the denominator at the beginning. So the denominator here was not rational. And now my denominator would be 1. So, and that is a rational number. So this idea of the conjugate, we can take the conjugate of any binomial. Remember, binomials have two terms. It has exactly the same terms as the original binomial, but the sign that we could say in the middle must be changed. So here my terms were 4 and the square root of 6, so I left it the same in the first fraction. I left it the same in the second fraction, but I changed the sign in the middle. So a plus b and a minus b then are conjugates of each other. The conjugate of a plus b is a minus b. The conjugate of a minus b is a plus b. What makes them special is what happens when we multiply conjugates together. A plus b times a minus b, that should look familiar. That's related to this idea of difference of two squares when we were factoring. And if I do FOIL, I see that that's what happens. I get a squared minus b squared. So if either a or b is a square root at the beginning, I end up getting a square root squared, which goes away. That's what happened here. 4 squared was 16. Square root of 6 squared was 6. And I really didn't need that stuff in the middle. So let's do a few examples of this. All right, so if I look at this and say, okay, the directions say to rationalize. I count how many terms are there in the denominator. I've got 2 terms, 1 and the square root of 7, negative square root of 7. So if there are 2 terms, I can't just multiply by the square root of 7. That's not going to work. If I multiply just by the square root of 7, I would have to distribute that and I'd get 1 times the square root of 7, and then square root of 7 times square root of 7 is 7. That square root went away, but I added in another square root. So that's not going to work. Let me get rid of all that stuff. Instead, I want to take the 2 terms in the bottom and just change the sign that's in the middle. So I change from minus in the bottom to plus in the bottom. And whatever I do to the bottom, I have to do to the top. So in the top, I'm not going to distribute yet. I'm just going to leave it written in factored form, right? 12 times something, those are factors. In the bottom, I can do FOIL. 1 times 1 is 1, or 1 squared is 1. Outer and inner, if you choose the conjugate, it's always going to cancel out. I'm going to get plus square root of 7 minus square root of 7, but that goes away. And then last, negative square root of 7 times positive square root of 7. Negative times positive is negative. Square root of 7 times square root of 7 is 7. And so we get 12 times 1 plus the square root of 7 in the top. 1 minus 7 is negative 6 in the bottom. I can cancel the 6 with the 12. 6 goes into itself once. 6 goes into 12 twice. So that's, let's see, 2 divided by negative 1 would be negative 2. So I don't have to keep the fraction anymore. I can just write it negative 2 times 1 plus the square root of 7, and then I'll distribute negative 2 minus 2 square root of 7. All right, just a few more examples. Okay, when I look at this next one, I see, all right, there are two terms in the bottom. I'm going to have to use the conjugate. So I'm going to keep the terms the same, but I'm going to have to take that sign that's in the middle and change it. So it's going to become square root of y minus 5. And whatever I do to the bottom, I have to do to the top. So I've got the negative 2 in the top. I get square root of y minus 5. And in the bottom then, when I do first, square root of y times square root of y, if I take a square root times itself, that cancels out. I'm left with just y. When I do outer and inner, they cancel out. Now, I'm writing it down. You don't have to write this down. Oops, square root. Right? That's outer and that's outer and inner. But those cancel out. All the time that's going to happen. And now at the end, positive 5 times negative 5, positive times negative is negative. 5 times 5 is 25. I can't cancel anything here, so I'll go ahead and distribute in the top. Negative 2 times negative 5 is positive 10. And just a note here, don't get cancel happy. I can't cancel y's here for a couple reasons. One, I can't cancel anything that's inside a root with something that's outside a root. So that can't be done. Second, and that's the thing here, I can't cancel the 10 with the 25. Now you might be saying, but wait a minute, 5 goes into 10 and 5 goes into 25. Yes, 5 is a factor of 10 and 5 is a factor of 25. But 5 is not a factor of the whole numerator or the whole denominator. This plus and this minus, those mess it up. I cannot cancel the 5's here. Don't get cancel happy on me. This really is all I can do in this problem. What would be different is if I had something like 10 times the square root of y over 25 times y. Then I could cancel and say 5 goes into 10 twice and 5 goes into 25 5 times. I still couldn't cancel the y's, but this plus and this minus means I can't do this kind of thing here. I can't do anything like that here because of the plus and the minus. All right, one last example. So again, I see I've got two terms in the bottom with radicals, so I'm going to use the conjugate. I'm going to take exactly the same terms, so square root of 5 and square root of 6, but I'm going to change the sign that's in the middle, so it's going to change from minus to plus. And then whatever I do in the bottom, I have to do in the top. We're going to have to be careful here. In the top, it may help to write this with parentheses. We're going to have to do FOIL in the top. We're also going to do FOIL here in the bottom. We're sort of used to doing that. Square root of 5 times square root of 5 is 5. When I do outer, I get square root of 5 times square root of 6. Remember, when you multiply two square roots together, you multiply their insides together. So that's going to be plus square root of 30. We really don't have to worry about that, though, because then when I do inner, I get the negative square root of 6 times positive square root of 5. That gives me that, and those things cancel out. And then positive times negative at the end gives me minus square root of 6 times square root of 6 is 6. All right, what do we have in the top? We have to do FOIL. So square root of 5 times square root of 5 is just 5. When I do outer, notice outer and inner are not going to cancel out here because they're both plus. So 5 times 6 is 30, so I get plus square root of 30. Inner, square root of 6 times square root of 5 is 30, so I get plus square root of 30. And then positive square root of 6 times positive square root of 6 is positive 6. In the bottom, I've got negative 1. When I combine like terms in the top, I usually put numbers first. So 11. Remember, what's really in front of these square roots are 1s. So 1 square root of 30 plus 1 square root of 30 would be 2 square root of 30 divided by negative 1. So that's really 11 divided by negative 1 plus 2 square root of 30 divided by negative 1. Or I could write negative 11 minus 2 times the square root of 30. We should at least think about, can I take the square root of 30 and simplify that? What are the perfect squares? 2 squared is 4, 4 doesn't go into 30. 3 squared is 9, 9 doesn't go into 30. 4 squared is 16, oh that's already more than half of 30. So there's nothing that I can do to simplify this, and that would be the answer. And that is sort of how we rationalize denominators, whether we have one term in the denominator or two terms in the denominator.